Hi, I'm Cherie, a PhD student at Carnegie Mellon's Robotics Institute. Today, I'm excited to present our work on 3D human reconstruction in the wild with collaborative aerial cameras. We are interested in accurate 3D reconstruction of dynamic actors in their natural environment. For example, we'd like to build a motion capture system to reconstruct the skeletal movements of this parkour artist moving through a forest. However, we see three specific challenges to developing such a mocap system. First, accurate reconstruction needs multiple viewpoints, which requires multiple expert operators to accurately control the cameras in space. Second, the cameras and vehicles' state estimations are often noisy, rendering inaccurate measurements. Another factor is occlusions caused by obstacles are frequent when tracking moving targets outdoors. These factors make manual data collection extremely difficult. We present an autonomous multi-camera system for 3D human reconstruction capable of tracking highly dynamic actors in the wild. At a high level, we first collect data online. Given current images from drone cameras, obstacle map, and camera robot states, our real-time multi-camera planner then outputs trajectories for each robot to follow. Here are some example footage of an actor playing soccer. Finally, the collected data are then post-processed with alpha pose, a key point detector, with triangulation to get 3D skeletal poses. We're inspired by many interesting works in the active viewpoint planning space. First, we find work that reconstructs static sites, often using an information gain formulation to maximize coverage of complex geometries. Second, we also find work specifically for human motion capture, where they use learning-based approaches to optimize for best viewpoints, but is limited to obstacle-free environments. Our previous work developed an autonomous aerial system to film targets amongst obstacles and occlusions given artistic cost, with the driving application as aerial cinematography. Most related to our work, we find a multi-robot aerial motion capture system that minimizes 3D target position uncertainty while avoiding obstacles. However, it plans for a short time horizon, does not avoid occlusions, and is focused on the actor localization task. Our multi-camera planning system needs to compute in real time, high-quality, simultaneous viewpoints amongst obstacles while staying safe. We break this to four main factors. First, maintaining safety, where the robots should not collide with each other, with obstacles, and with the actor. Second, 3D reconstruction requires multiple viewpoints. We must therefore penalize possible occlusions, such as this tree, to maintain actor visibility. We also need to reason on the post-processing system, where key point estimation is most successful when the majority of the body is in view, thus requiring a load tilt angle relative to the actor. Lastly, given limited UAVs, we would like to maintain relative yaw angles between the robots to give good triangulation performance. Given the above factors, we formulate a trajectory optimization problem to find a set of smooth trajectories with minimal total cost. This is represented as a weighted set of cost functions that balance motion smoothness, occlusion avoidance, and robot safety. In addition, we introduce an additional objective, J-form, to maintain a good reconstruction formation. To optimize in real time, we planned a set of trajectories using a two-stage approach. First, we predict an actor path and plan discrete formation paths over a long time horizon. Then, each drone smooths its trajectory with its decentralized planner. Now let's dive into details. To obtain an actor forecast for long horizon planning, we first detect the actor using a MobileNet V2-like network. Then we project and raycast the estimate from image to global space. Finally, we predict the actor's future path with an extended Kalman filter. We plan formation trajectories using a spherical state space centered on the actor's position. To minimize the skeletal post-reconstruction error, the ideal camera formation should maximize the angular distance between the multiple cameras to minimize triangulation error, while keeping a low tilt angle. To reason about the role of obstacles, we first transformed the occupancy grid into our spherical space. The obstacle cost is then the sum of occupancy within a given radius of each UAV. In order to maintain target visibility at all times, we calculate the occlusion cost as an occupancy sum along a line between the UAV and the actor. Intuitively, we wish to minimize the penetration of a line between the camera and the actor, which is inside obstacles. Given the centralized planner cost for all robots, we optimize the discrete paths with dynamic programming. In this work, we lock relative drone position given desired tilt, range, and the relative yaw angle between robots. This allows us to only find the optimal yaw angle sequence over t time steps. We then build the cost map given where each drone would be if the formation is at a given yaw angle. Then we calculate optimal cost to go by backward induction. Finally, we build the full yaw sequence by selecting neighboring cells with the least cost to go. With the discrete viewpoints, each UAV optimizes and smoothens its own trajectory using an individual camera trajectory optimizer from our previous work. Here's a quick recap of how our planner is used in the full reconstruction system. We evaluate our system performance using AirSim, a photorealistic simulator that also provides ground truth skeletal mesh. We first quantify the benefit of maintaining a low tilt angle for reconstruction by varying a two-drone system at tilt angles from 0 to 60 degrees. With no noise, high tilt angle yields worse in reconstruction, likely because a large portion of the actor's body is occluded by itself, and possibly due to the lack of training data at high angles. We also see lower tilt angle is more robust to camera noise. We then validate our method scalability to at least 5 drones. Then we examine the impact of more robots to reconstruction accuracy, showing more robots improve both reconstruction quality and robustness to noise. We test our approach with 2 drones. All planning is done on board with the formation planning at 10 Hz over a 10-second time horizon, taking less than 2 milliseconds. Here we see our approach coordinating 2 drones tracking an actor for reconstruction while avoiding a mount. Here shows a time lapse of the previous trial. As the formation rotates around the mound, it is able to maintain a low tilt angle. We see our formation planning renders consistent skeletal reconstruction. We compared our method to a fixed formation that does not rotate. Without formation planning, the robots go upward to avoid the mound, reaching a tilt angle of around 60 degrees. As seen in simulation, the skeletal's key points fails often for these footage, resulting in poor reconstruction. Finally, we showed a 3D reconstruction of a highly dynamic real-life actor jogging and playing soccer. Our system is able to keep up with abrupt motion changes while maintaining good formation angles for reconstruction. In conclusion, we presented a multi-UAV system for 3D human reconstruction in the wild. We show our formation planning improves reconstruction quality while avoiding obstacles and occlusions. Finally, we validated our system in the real world by reconstructing an actor jogging, walking, and playing soccer. We are excited to be building upon this work towards high-fidelity reconstruction of multiple actors. Active work includes shared multi-robot, multi-actor detection and tracking, adaptive formation planning for high-fidelity reconstruction, and finally, extending a current single-view human depth estimation to our multi-view framework. Thank you.